We are supposed to now make use of the method of mathematical induction to prove the expression for Pn to be 1/3 7 minus 4 to the power of n. Well, I'm going to write down my proposition. I'm going to call it Pn, which is small pn, where it is equal to 1/3 7 minus 4 to the power of n, where the question gives me that n is supposed to be bigger or equal to 1. The next step of mathematical induction is to go for the smallest possible n and prove that it is true. The smallest possible n is 1, so I'm going to go for P1. And on the left hand side of P1, it is this small p1, and this is equal to 1 because the question gave us so. Okay, so the next thing that we need to do is to prove that the right hand side is also going to be equal to 1. So on the right hand side, it is 1/3 7 minus 4 to the power of, replacing n by 1. So 4 to the power of 1. 1/3 multiplied by 3. This is 1. This is the same as the left hand side, which means that P1 over here is true. But of course, we know that this is not enough, because if you want to show what we need to show, it is not just P1 to be true. We need to show that for all n to be bigger or equal to 1, they are all going to be true. That means P2, P3, P4, everything, right? They are all the way until infinity, they are true. Right? Rather than doing it manually, right, which is not really possible because we are going to find n all the way until infinity, what we are going to do is to use this very elegant process, which is the method of mathematical induction, because the next few steps are the key to mathematical induction. We are trying to prove a relationship next. We are trying to prove that as long as this current term or this current expression is true, it's going to cause the next expression to be true. That is why after we have proven that P1 is true, we are going to just simply assume, without really proving it, I'm going to assume that Pk is true. But of course, not for any k, but for some k that is also going to be bigger or equal to 1 or positive integer. Which means that I'm assuming that if it is Pk, this is going to adopt an expression of 1/3 7 minus 4 to the power of k. This is my assumption, and what is my aim? My aim is to make use of this assumption to prove. To prove that the Pk plus 1 proposition is also true. Which means that I'm trying to prove that Pk plus 1 is equal to 1/3 7 minus 4 to the power of k plus 1. Okay, this is my aim. And how do I achieve this aim? I'm going to make use of the recurrence relationship that is given to us. It is given to me that Pk plus 1 can actually be rewritten as 4Pk minus 7. And this will allow me to bring in the Pk proposition into the Pk plus 1 proposition that I'm trying to show. Because this is how I'm going to try to establish the relationship, okay? Because this is not something that I've proven true. I've only assumed that it is true. But what I'm trying to prove, right, is that this one can be true as long as the previous one is true. And that can be done by making use of the recurrence relation that the question has given to me for this sequence. Okay, so from here, it is 4 multiplied by Pk, which I've already assumed true. It is 1/3 7 minus 4 to the power of k, then minus 7. Since this is what I want to achieve from this expression that is here, I see that there's a 1/3. Okay, so I'm going to factorize out 1/3. So 1/3, which means that what I'm going to be left with inside it is 4 multiplied by 7 minus 4 to the power of k, and this is minus 7 times 3, so minus 21. Okay, so this is 1/3. Multiplying in 28 minus 4 to the power of k plus 1 minus 21. And this is 1/3, 28 minus 21, 7 minus 4 to the power of k plus 1, which is the expression that I was trying to aim for. What does this show me? This shows me that as long as the Pk proposition is true, it's going to cause the Pk plus 1 proposition is true. That's why I'm going to say something that is like this. Therefore, the Pk plus 1 proposition is true if PK proposition is true. Okay, we have established that relationship that the previous term is going to cause the previous proposition is going to cause the next proposition to be true. And that is why if we have already shown that P1 over here is true, okay, which we have done it manually, okay, since P1 is true and plus making use of this relationship, it will tell me that P2 is true. Because P1 is going to cause P2 to be true. Then P2 will cause P3 to be true. P3 will cause P4 to be true. That means everything, okay, from n is 1 all the way until infinity, they are all going to be true. Okay, so since P1 is true, by making use of this process, by making use of the mathematical induction, I can say that Pn over here is true for all the n's that are bigger or equal to 1.